Sharing the wrong screen there. Hang on, guys. Sorry here. Let's see. Can we share the screen instead of the application? Can you help me share like screen here? I'm not sure how to. I don't want to turn off. All right, I'll just keep going. I've lost my presentation. Sorry. Here we go. Okay, so then we're trying to follow these patients with care coordination software. They're going to get echocardiograms twice a year, lifestyle modifications, sometimes antihypertensive medications, but some of them are going to go on and get like coronary stents, cabbage, valves replaced, pacemakers, and defibrillators. So these are big ticket items that have been shown to markedly improve overall survival. So besides helping the patients, there's a potential financial return on investment then. If we could just capture 25% of these patients using this system, so maybe we call all 4,000 of them, but only 1,000 of them show up into the clinics, that's $20,000 per patient in terms of Medicare dollars, and that's $20 million over the course of their lifetime. And that's every single year that you're going to recuperate that money. So this has a potentially the highest return on investment that I've seen potentially for opportunistic screening in any one particular algorithm. So this is what our algorithm looks like. Like I said, we're measuring the cardiothoracic index. So we're automatically detecting that heart, automatically detecting the inner chest. The traditional cardiothoracic is a linear measurement, which we can actually calculate, but we actually think the area-based one is going to be better because the heart can enlarge in multiple different directions. How we train something like this, we actually use outside CTs that were obtained at centers that are outside of UAB, but were imported into our archive. And that way you incorporate a lot of the heterogeneity in the way that the scans are done and in the patient makeup for that. And so we particularly enrich that for difficult things. We tried this first on using patient data that had clinical trial data and found when we actually applied it in real life scenarios, it failed. They would have problems with pericardial effusions, pneumonia, hiatal hernias, elevated diaphragms, pacemakers, and other devices that might be in that scan were interfering with our ability to do this. So we now enriched specifically for those difficult cases. And we have a technical validation data set from entirely different institutions. So we make sure it's not a split cohort. We use like institutions 1 through 30 for training and 31 through 50 for validation, and really got really high DICE scores. This is a measurement of overlap between a human annotating the data versus the AI, and really got high metrics for being able to do that. So this is moving forward. This is a clinical validation study that we had comparing on the left, the AI cardiomegaly, breaking it into 3 different groups versus manually measuring the cardiothoracic index. It turns out we outperform the manual measurement. That's not really the goal. It just happens that we have that nice little bonus that we did outperform it. The goal was really just to fully automate this. No one wants to measure 80,000 patients a year doing this thing manually. Now we're able to do it in a fully automated way and detect that they have a 4 times fold risk of future cardiovascular disease events if you have cardiomegaly. So I like to think about this from the commercialization standpoint. The invention part is when you think of the idea. We submitted a patent. That patent is pending right now. It hasn't been issued at this point. But we're pretty good at getting these 20 plus in the same space. So we're probably going to get that patent. Innovation is when you're actually creating it and working to develop it and move it along before you spin it out into commercialization. So we got a grant through UAB. We've applied for a small business grant at this point. And now we actually formed a small business company related to it. We're seeking FDA clearance. Our goal is to submit that FDA application next month. If we do that, based on our experience, we've got quite a few of these algorithms cleared in the past. We'll probably have it by the end of this year, FDA clearance for it. It's called a 510K pathway for doing that. We're also exploring other ways of doing this. So I showed you the chest CT. You can certainly do this on a chest X-ray. So we have teams that are annotating the heart and the entire chest, the inner chest, doing this on chest X-ray as well. And that's just more preliminary. We haven't trained that model yet, but you first have to get the images and annotate the images. So we're going through that process right now using similar mechanisms. I want to show you just another example. So a different way of screening for data and pulling it out of existing visits. So this is visits for if you came in for appendicitis and you just happen to have a CT scan, we can do some very interesting things with it. It's very normal. In this case, they didn't have appendicitis, but they had a big aneurysm. It's not what was causing their abdominal pain. And we report that universally as radiologists. Not hard to find this, easy to report it. The problem is that 18% of these never go under management. So it might be that they don't have a primary care physician here, or even if they do have a primary care, there's just loss of information between that report, and sometimes it doesn't make it even into the impression. Even if it did, we don't follow up on all of these patients. So that leads to ruptured aneurysms. This has been shown in multiple different centers that people will die just because we're not following up on this correctly. How can we circumvent this process? So instead of using AI to actually find the aneurysm, which you can do, we're taking a different approach. We're using natural language processing to screen all of those reports for these aneurysms, and then we put them through the care coordination work list. This work list goes to the cardiovascular surgeons, and they work this up. Now, it's less patients per day than cardiomegaly. 2 patients a day is what we're expecting to find that are unmanaged. AAAs, which are abdominal aortic aneurysms. And then these are going to undergo surveillance and repair as needed. So this is, again, a potential life-saving screening method to do this, and it has a financial return on it on this. We think about half of these patients will probably show up, because if you tell someone you have an aneurysm, they're probably going to want to go see their doctor about that. That's about $10,000 per patient, which leads to a return on investment on a yearly basis of $3.8 million. So what we're trying to do with commercialization is help patients, and you have to have a financial return on investment, or no one's going to use it. So I'm getting to the end. I think it's my last slide here. So we're going to build and aggregate the best fully automated AI and NLP algorithms for opportunistic screening. Our example on chest CT or chest solutions was the cardiomegaly. We're also doing NLP on aortic aneurysms, but the reality is you can do this across multiple different things that are in the cardiovascular space. Sometimes it's in lung disease like emphysema, or it might be something like liver fat or cirrhosis. So our hope is to be able to develop the rest of these algorithms over the next year using cardiomegaly as our template. So we're co-developing this and licensing with servicing providers, and we're seeking FDA clearance. We think we'll have our first clearance by the end of this year, and probably multiple other ones across the next year. Many of these algorithms have actually been built by other people, and we're going to license them and package them all together. So we're going to maintain a quality management system and sell through distributors, which avoids development of a sales team. So it's a really nice structure for a business where you don't have to have an actual sales team to be able to do this. These are my teammates that are helping me with this. Stephen Rothenberg's a chest radiologist here, has a lot of experience. He developed the first AI marketplace in radiology. And then Yujan has over 30 plus FDA cleared products. And this is just another one that he's going to add to his list. So we're really excited to move this technology forward. And I appreciate you guys listening to me.
Yeah, we have time for one question at least. One question.
Sure. So this comes back to like what Trey was saying about like transparency and things. We want it to be extremely transparent numbers. So rather than the probability, we actually give you the cardiothoracic ratio, and people can use that information to make decisions. So very transparent numbers. It's a very clear number that people are used to, that's very well validated in the literature. So he was asking about integration of this. Of course, it's challenging to integrate any of these AI algorithms into the workflow, but thankfully in radiology, it's pretty common to do these fully automated algorithms, direct all the CT scans to a server and process them. So challenging, yes. So is it solvable? Absolutely. We've already solved it and are doing this right now at UAB.
One quick question from Jeff. Yeah, sure. Yes. Yeah.
How does FDA approve the unfinished product? So they need to, he's asking about FDA clearance, so they need to approve something that is finished. And in this case, like an FDA 510K clearance means you're going to point to another algorithm that's very similar. So we point to something, sometimes it's not even an AI algorithm, but something that measures the heart and does so. And all we have to show is that we're measuring in a similar way. So we usually go for very low hurdles to start for the FDA. Just show that we can measure something, let the clinician make the decision, rather than say we're going to predict who's going to get a heart attack or something like that. That's a much higher bar to get FDA clearance. Just saying we measure something the same way that a human measures it's very easy to document. I'm going to turn it over.
Okay. All right. Thank you. Thank you, Andrew. So our next speaker is Dr. Sotoudeh. He will present on the radiomics and the role of AI in medical imaging. Dr. Sotoudeh is the Director of Radiology, Clinical Research, and Associate Professor of Radiology and Neurology at UAB.
Good morning. Thank you, everybody. My talk is about a brief discussion about the radiogenomics and the role of AI in medicine and medical imaging. I have no conflict of interest. If you look at, if you look at the history of AI in medicine, every year there are more and more publications. These days, essentially, it's not possible to understand the medical literature and papers without basic knowledge of artificial intelligence. So far, by the end of 2022, more than 520 platforms and applications regarding medical AI have been approved by FDA. If you look at these platforms, almost 75% of them are related to the radiology. So right now, so far, radiology is the leading field of medical AI research in clinical and research development. If you look at the AI and the different models of the AI, there are two big families of the machine learning and artificial intelligence. One family is shallow learner. They are traditional machine learning models. They are essentially predefined rules and formula to analyze the features and data. They cannot analyze the complex and big data. And the features should be first engineered. Then these models are able to consume these features and to do the prediction. Linear regression, logistic regression, decision trees, support vector machines are the most common form of shallow learners in the first family of the machine learning. As I mentioned, they are not able to handle the complex data sets and they need feature engineering before the machine learning. The second family of machine learning and artificial intelligence are deep learning. These models are a mimic from the human neurons, and they are capable of analyzing and working with the deep complex features. The most common models belongs to the deep learning models are the convolutional neural networks and natural language processes. And right now, most of the development of in the medical imaging and artificial intelligence are the field of the deep learning AI. So as you know, and you are familiar with the neural networks, these neural networks consist of one input layer and one output layer. Between these two layers, there are multiple of hidden layers, and data is analyzed level by level from the input layer to the output layer and then to the prediction layer. The big family of the machine learning model in medical AI is image classifier. They belong to the convolutional neural network. At the core of the convolutional neural network is the neural network. However, for the analysis of the images, neural networks are not capable of capturing the data as a raw images. We have to manipulate the medical images in a way that it can be understandable to the neural network. And this manipulation is done by different steps called convolution, ReLU, and max pooling. At each layer, we are going to make the medical images simpler, and eventually we are going to convert images to the simpler, smaller images, which can be used for the machine learning and neural network for prediction. Here is one example of the machine learning module which we use in the clinic as a detection of the blood hemorrhage. As you can see, subdural hemorrhage in the right cerebral hemisphere and right tentorium. Convolutional neural network is going to manipulate the images and finally feed it to the neural network to get the classification of the hemorrhage or non-hemorrhage and then image segmentation. The next big family of the machine learning models for the radiology is the image segmentation module. They are a variation of the convolutional neural network. They constitute of two different convolutional networks. The first limb is going to contract the images. It's going to manipulate the images to a simple model. And the second arm is going to expand the model in a way that they can reconstruct the images one more time. By doing the contraction path and expansion path, we can put the marker and segmentation over the lesion. And these models, as you can imagine, the shape is the shape of U. They are calling the unite model. They are very robust neural network models for image classification plus segmentation in the radiology. So if you look at the current application of the deep neural network in the radiology, we can do image classification and avoid misdiagnosis. We can triage the patient in our workflow. We can move the patient to the top of list in case of urgent finding on the radiologic images. The model can do image segmentation for us and save a lot of time. We can do computer aid detection for the radiologic presentation, which are very difficult to be diagnosed by human. For example, pulmonary nodules, which are small or small lesions in the mammogram. We can use computer-aided detection for improving the diagnosis. We can do quantitative analysis. These models are capable of segmentation and then volume calculation, and they are going to save a lot of time for the radiologist. Overall, these models depend on the neural network. They can help the radiologist with low expertise. National language processes can generate report and impression for us. Again, they can save time. Right now, we use the same model for our daily practice, and these models are capable of analyzing the body of report and generate the impression in the report of the radiology exam, and they can improve the efficacy of our radiologist. And one big part of the medical imaging and neural network is image reconstruction. It's very important in the clinical radiology. We can implement neural network in the image acquisition and image reconstruction phase. These models can reduce the radiation dose in CT scan and PET scan, and they can reduce scanning time, especially in the MRI. And overall, they can increase the workflow and radiology efficacy, and they can reduce artifact in the clinical radiology. And eventually, neural networks can optimize the radiology application in the daily clinic. Finally, they can improve the efficacy of the radiology department. So the question is that what is the role of shallow learning? To answer this question, let's look at this example. Both of these patients are pituitary macroadenoma. Radiologists and neural network can predict the diagnosis and classify and segment the pituitary adenoma. However, there are many more questions. What is the proliferation index? What is the gene mutation? Which one is hard or soft? What is the chance of recurrence? What is the histopathology? If you look at the maximized view, it seems that the texture of these tumors are not the same. At this time, neural network and the human radiologists are not able to answer these questions. Same thing for the meningioma. We have two meningioma. Both of the radiologists and neural network can predict the chance of meningioma, and they can segment and measure the volume. But the question is that what is the grade? Proliferation index, doubling time, which one is radiosensitive? What is the chance of recurrence after surgery and chemotherapy? Again, if you maximize the images, it seems that these two meningiomas are not the same. And here is the role of shallow learner models, and we call it radiomics. These old models these days are able to do the texture analysis. They are a new era of precision medicine. And the concept behind the radiomics is that these medical images contain many more information which are hidden to the human radiologist. By analyzing these features, we can provide more information regarding the clinical data. Radiomics has 4 steps: image acquisition, segmentation, feature extraction, feature selection, and then shallow learning, machine learning. And by using those models, we can predict the gene mutation and histopathology. For example, in pituitary adenoma, we can do the gene mutation and histopathology in the pituitary lung cancer. We can do the same thing, tumor response for meningioma. We can predict the gene mutation and glioblastoma. And in the PET scan, we can do the same thing for lymphoma, predict the survival rates and treatment response and prediction. Radiogenomics is a subtype and a branch of radiomics, which we try to predict the gene mutation and genetic profile of diseases based on the radiomics. It's not limited to the oncology. Various diseases, including cardiovascular disease, psychiatry, and neurologic disorder can be also involved and evaluated by radiogenomics. And the teaching point of my talk is this slide. At this time, the radiology is the leading field of medical AI. 70% of research and development is in the medical imaging, in the medical AI. Deep learning is the most important part of the medical AI radiology at this time. They can improve our efficacy. However, as you see in this field, we are in good shape in the research and publication and development of the deep learning model in radiologists. We can do computer-aided detection, workflow optimization, image classification, segmentation, and generation of the report and impression. So we are doing fine at this stage. By using the deep learning, these platforms eventually can improve our efficacy as a radiologist. However, on this part, shallow learning models and radiomics, we can do texture analysis, we can predict histopathology, we can predict the gene mutation, and clinical data point, for example, survival rate, treatment response, treatment side effect, and eventually we can design more personalized medicine. This area is the area of many opportunity at this time. There are very few publication and development at this area, and eventually if we can do study, and that's a very good start point for adding one more dimension to the clinical imaging. By this, I'm done with my talk, and thank you very much for your time. If any question, I will be happy. Okay, thank you very much.
All right. Okay, so our next speaker. Our next speaker is Dr. Matthew Might. He is professor of precision medicine and also the director of precision medicine. All right, thank you for coming.
All right. So there we go. Oh my gosh, it worked. I think this is the third time I've used this trick at UAB. So it's great to be in person presenting over Zoom. It's just how it is these days. All right, so I think this actually perfectly dovetails with that last talk, because this is sort of a deeper dive into how AI applies specifically in the context of precision medicine and the kinds of things that we're doing in the Precision Medicine Institute here at UAB. And what I want to do is try to illuminate it for you in the context of individual patient stories to show you what does it look like when you really bring everything there is to bear in something like modern AI into the life of a single patient. Now, before I get going, the UAB Office of Legal Counsel always requires me to say this. If there's anything in this talk that resembles medical advice, don't take it. I am not qualified to give it. So we have a complex return of results process in place within the Institute to protect patients. And I say this because there's a lot in this talk that will look like medical advice. And even more interesting is that 100% of that advice is actually computer generated. So with all that in mind, yeah, I'm actually a computer scientist. That's my original training. I spent most of my academic career actually doing things like cybersecurity, working on supercomputing and domain-specific language research, supercomputing, in my home field of automated reasoning in the context of programming languages, which has a lot of relations to, good old-fashioned AI, as they call it. So today, with 15 minutes, I just want to get one thing across, and that is, what does AI in precision medicine look like in the context of patients? So let's just rewind a little bit. What is precision medicine? And again, short-circuiting to the answer, I tend to think of it as everything that falls into the banner of optimizing health with data. And this shares a number of natural correspondences, as you'll see in a second, with machine learning and artificial intelligence. So we think of it as a process. You're mapping a patient or really their data over to the set of best possible treatments for them. And the piece of data that got everybody super excited at the start was the clinical accessibility of the human genome. It's a massive piece of data that requires significant computation to wrangle. So now, if you really want to find the best thing for your patient, you have no choice as a physician to either directly or indirectly interface with some pretty significant compute. But there's other data out there still that has been out there that's still not fully exploited. There's all the longitudinal data sitting in the EHR. And I can guarantee you, there's no health system in the world that has yet fully exploited and optimized what can be done with even that data, even before we get to the genome. And then there's all the data outside the patient, all the knowledge sitting in published papers and textbooks and biomedical data sets. All of this can be brought to bear as part of an optimization problem. So I think if you put it all together, what you do get is you get this constrained optimization problem, and you are trying to modulate things like treatment and lifestyle to achieve the optimal health for any given patient. And so if you are a machine learning expert, now you know it's just gradient descent, but in a very complex space. Really, this is the equation. It's all about combining lifestyle and treatment to find optimal health. And there's two parts of this. There's the diagnostic phase where you're searching for that root molecular cause. And in the context of something like rare genetic diseases or cancers, genomic sequencing does in a lot of cases allow us to jump straight to it. But even for something as complex as diabetes, we can start to unravel individual molecular mechanisms in the context of an individual patient with some of the newer omics modalities. It's becoming possible now for almost any disease. And I'm going to skip over precision diagnostics today, because I think one of the things that's really exciting about UAB is that we have a number of folks focused on what comes after, precision therapeutics. And there's really two approaches at a very high level you can take to doing this, to personalizing treatment like that. And are frozen. All right, is that better? Audio is back. Okay. All right. So again, you can try to rationally invert the mechanism of harm. That's what we're trying to do. And there's also an empirical approach. So actually Brad Yoder and I, we co-direct this center here at UAB called the Center for Precision Animal Modeling, where we do lots of genomic engineering on animals and make precision disease avatars, and we can do drug testing and things like that. I'm not going to talk about that today, because there is AI involved even in that. It's just not, the main driver for that work. So what does it look like in the context of individual patients? I've just, pulled out a handful to show you from folks that have reached out to PMI. I do have to acknowledge, of course, that we do a lot more than this. There's a really broad team in place for the leadership at PMI. We're active in areas from oncology to metagenomics and infectious disease to pharmacogenomics to data science. I mean, there's, and Bruce has a long history of work also in personalized therapeutics and in infection or in precision diagnostics. I can't cover all that in this short time. But what I can do is talk about the science and the service of patients that we are able to do, much of it enabled by and only possible through AI. So we have an amazing clinical team that double checks everything the AI says, make sure it's not hallucinating or lying. And a large team of undergraduates, actually, and now med students that sift through some of the results that come back and distill them into cogent reports that are meaningful to physicians. So I'll just give you some stories, and I'll start with Kelsey's story. And I like starting with hers because there's no genomics involved. It's just better use of existing data. She was 19 when her parents reached out, sadly suffering from pretty severe cyclic vomiting syndrome, to the point where she was frequently in induced coma, and despite being 5'4", was 75 pounds. So she was suffering from dozens of vomiting episodes per day. And of course, her parents or clinical team, they said, we've tried everything. This is essentially the admissions criteria for PMI. You have to say this to get in to our research program. And everything in this case was about 25 things. That's a lot more than we typically see. But when you actually read everything out there, there's some stuff that was missed. So we read all 30 million published papers at the time, biomedical papers, that is. We found 64,000 on treating nausea, and about 4,000 or 64,000 on nausea, and of them 4,000 on treating it. And between those, there was 347 different proposed treatments for just nausea. And at the top, if you do this sort of as a histogram, there's Zofran. There's 169 papers that say Zofran is something you can do for nausea, not a surprise. But if you zoom down the long tail, you get to really interesting stuff, like nasally inhaled isopropyl alcohol, where there's 3 papers talking about this in a clinical context. And so we sent 3 papers back to Kelsey's team, and they said, okay, well, we can try it. It'll be fast if it's going to work. And it did. It actually did. In fact, it worked immediately. And she's been able to stop every episode of nausea ever since using this relatively simple trick. But 8 months after this, her mom wrote, say, hey, she's better. She's up to 125 pounds, and she got married. Her high school sweetheart had been visiting her every day in the hospital. And once she recovered, he proposed, they got married, and they moved to California. So last I checked in with her, still happily ever after. But again, no genomics involved to do that. And when I say we read everything, of course, I don't mean the undergrads. I mean natural language processing. So the early versions of this were all built on SemMedDB, still a very useful resource for us, actually. Even today, it's a natural language processing distillation from the literature. So can we do more? Well, absolutely. Once you've got something like the literature plus all these other biomedical data sets wrangled together, you can start using logical inference to infer things that no paper cites, in fact. So for example, we built a tool called Betty Cannon, funded by NCATS, and it really is a fusion of logical reasoning and all the biomedical knowledge we can get our hands on. And in a nutshell, it's a fusion of old school logic, high-speed automated reasoning, to achieve superhuman-like deduction with clinical insight. Now, the clinical insight part is not quite there yet. That's why humans are still very much in this loop. But that's the goal. That's the ambition. And I can even show you what does its brain look like. And I think this is actually important given the previous talk where you looked at the guts of a neural network. This is not a neural network, although we do use lots of neural networks in other parts of our work. And so if you peer in the brain, you see a bunch of circles. And the circles are actually just nouns. They're biomedical concepts and biomedical knowledge. So genes, drugs, diseases, symptoms, things like that. And then there's edges between the circles. These are verbs, predicates, relations. And every time you draw one of these edges, you form a sentence. You form a fact in the brain of this thing. So for example, you can encode the sentence, the knowledge, preface it inhibits endgaze by just drawing this edge between these concepts. And then you can make inferences, logical inferences. So if you know, for example, blue increases red and red decreases green, you can logically infer that by increasing a decreaser, blue should also decrease green. Well, 5 minutes. So we're on perfectly on track. Perfectly on track. Okay. So that's the guts. Well, that's the brains of Cameron, which is quite distinct from a neural network. Yeah, it's very different model, but they're highly complementary, and I'll get to that at the very end. So you can ask it questions like, hey, what treats why? And it's got creative mode now where it can try to come up with different suggestions for how to do this. Or you can do what we do 75% of the time, which is just say, I already know what I want you to do. This is the target. This is the direction it needs to go. Just tell me how to do it. And that's mostly what it does. And then you can start applying it. So for example, there's a genetic autism caused by a haploinsufficiency in ADNP. The mom, who I've known for years, reached out shortly after I got here while I was building this tool, early on. And she said, hey, can it make any predictions for ADNP driven autism? And I said, well, let's just ask it. I said, what upregulates ADNP? What activates this? And it came back with low dose ketamine. In fact, there's 2 papers out there in total showing a pretty strong effect here. And we pulled them out, we sent them over to the chief scientific officer for the foundation. They actually used this to get a clinical trial launched. They had the worst timing in the world. They launched it in February 2020. Then the pandemic hit. They gave us, a lot of credit for enabling this to even start. And then of course, COVID slowed things down, but they didn't stop. They actually did finish launching the trial and completed it by last summer. And remarkably enough, when they looked at tissue samples from patients, they did see a normalization in ADNP. More than that, of the, I think, 14 endpoints they were looking at, 13 of 14 showed statistically significant improvement. But even more than that, it showed a big difference in the lives of the patients. So if you look at this article in Stat from about a year and a half ago, it describes what this meant from the patient perspective. If you want to know about what it meant from the scientific perspective, we published that last fall. Last case I'll show you is driven by hyperactivity in a potassium channel, KCNMA1. If you've seen the Netflix show Diagnosis, this is one of the episodes, in fact. And so this girl here, she was the first case ever discovered of this particular disorder. So first patient in the world. And she was suffering from on the order of 150 cataplexic episodes per day. So this is a lot. And, significant risk to her life, significant impairment in quality of life as a result of this. So what did Cameron say? Well, again, because it has no sense of humor, it says, well, why don't you just give her crystal meth? She will feel so much better. And the truth is, it had a logical basis for this. And the logical basis was methamphetamine is an inhibitor of KCNMA1. That's the rationale. And we were nervous enough that we didn't jump on it right away, but eventually
some drug discovery thinking that I've been doing for the year. Yeah, I think it's right now we're building it manually. We're starting from the pager database that has lots of connected networks and genes. There are public databases like protein interactions, and then we just need to build a pipeline. But eventually, I don't see any reason why we cannot do the map in a day. But right now, it's a couple of weeks.
Thank you, Jake. So our next speaker is Dr. Zhang. Dr. Zhang is a director of the Center for Computer-Aided Drug Discovery at Southern.
Thank you for the introduction. And good morning, everyone. Thank you for inviting me for the talk. So I think I should share it with Zoom first. Yes. Can you help me with that? So my talk today is AI-aided drug discovery. It's kind of a continuation of the concept Dr. Jake Chen just said, but it's like more on the early stage rather than the clinical phase. And I also see many interesting talks early today, so I'm looking forward to the rest of the day. In my talk today, first, let's have a very brief overview of the integrated platform we established for AI-aided drug discovery. And then I will show you two research projects from this platform. So this platform, the SAGE platform in Southern Research, is integrated platform that's for AI-aided drug discovery. So we integrated both wet bench capability as well as in silico modeling tools. And we use our in-house generated data to build AI models, and we use those AI models to facilitate the drug discovery pipeline. So this shows you a brief, the overall picture of this platform. Besides our in-house capability, we also love to collaborate with many other external partners that we together can build a powerful drug discovery platform together. So briefly, in this integrated platform, we can start first with biology. We have a biology team. They develop a lot of either in vitro or in vivo assays for many different disease therapeutic areas, such as oncology, neurology, infectious disease, rare disease, and other therapeutic areas. So once we have these assays, it can be optimized into the high throughput screening fashion. In our high throughput screening center, then they can screen maybe millions of compounds to generate millions of data. And those data, we have an in-house database that will format all this data to make it ready to be used as the training set for AI model. And since they are many of them, they are phenotypic screening data, so we can use those data to build our in-house AI model to predict phenotypic activity. Similarly, we also have a bioanalytic lab. They also generate tons of data of pharmacokinetics and drug safety. So those data will also go to our digital database, and then we use them to develop AI models and to predict pharmacokinetics and drug safety. So on the other hand, we also have in silico tools. For example, if we use some bioinformatic tools, then we can help to find out some therapeutic target or biomarkers for different disease. Once we know certain therapeutic target for disease, then we also have some molecular modeling tools. Those they can model the interaction between the drugs and the protein on the atomic level. So this is different than the AI model. That it will study the same thing from a different aspect. And on the other hand, we will later also have those AI models to predict other aspects that we care about for the drug discovery. So altogether, using this AI model trained by in-house data, we can design some new compounds, and we also have our medicinal chemistry team. They can make the compounds we design, and then those compounds will go back to be tested, and the data, experimental data collected from those new compounds will again feed back to the model. So because these AI models, when they learn more data, they will be more accurate. So we do this drug discovery in an iterative fashion, and eventually we will have some good preclinical candidates. So besides our in-house capability, as I mentioned, we also like to reach out to all the external collaborators to build all this drug discovery platform together. So for example, for biology assay, we actually also have many collaborators. They contribute assays for many different diseases. And in terms of bioinformatics or clinical database, actually, for example, UAB also have many useful resources such as UBright, the pager, and also other informatics tools that we hope we can have some synergy with our drug discovery platform. Besides, we also want to have other external collaborators for additional in silico tools and wet bench capabilities, like some of the tools presented earlier today, such as those predict the protein-protein interaction, or the Medicarin, which can help search the targets. They are all very useful for this purpose. Lastly, Sotoudeh Research also have a commercialization platform. Once we have some good preclinical candidates, then we can commercialize them to try to have funding for clinical trial. And again, AI can also be used to design clinical trial, but I think that will be another story for another day. So for today, let's focus on the early stage of drug discovery. So we have built many phenotypical prediction models using AI algorithm. And here I showed you some example. So that's why when we using in-house data, it gave us some advantage. So like in this example, we have some better theoretical accuracy than the other model if you only use literature data. But that's just a theoretical accuracy. So we also want some real world validation of those models. Currently, we apply those models, like in this example, we predict the solubility and the metabolic half-life of the compounds, which are two important properties if you want to develop already available drug. In our AI model, solubility, the accuracy is about 83% when we compare it to the real experimental data we obtained later. So like a popular software in the industry, the accuracy is about 60%. So indeed, our AI model can better help the medicinal chemistry to design compounds. And similarly, the stability model, the accuracy is 88%, which is also reliable enough. So besides, we also developed a friendly user interface. Currently, it's in the testing phase, but the general idea is that in the future, our users, they can just upload the chemical structure they want to get the prediction, click the predict button, and it will return them the results. So currently, we use those are the platforms we established, and we are currently applying it to many projects, such as the antiviral project. We use it to predict antiviral activity, pharmacokinetics, and off-target toxicity. In this example, is we have a project to discover new anti-flaviviral agents. Flaviviral is a tropical viral that currently do not have FDA-approved drug to treat. For this project, we previously performed a high-throughput screening of 200,000 compounds. So from those high-throughput screening, we already identified 2 good compounds, and they are currently in development. However, we also want to identify a 3rd compound as backup, because just in case the first 2 failed in preclinical evaluation. Then we use those 200,000 data. We build an AI model to predict the anti-dengue activity. And once we have the model, we virtually screened 1 million commercial compounds, and we selected 48 of them for the actual assay to test. And 26 of them turned out to be really active. And among them, one of them is very potent. So we discovered a 3rd backup good compound for this project. So if you do a simple math, for the initial effort, roughly you need to screen 100,000 compounds to get 1 good compound. However, if you want to discover more compounds, you no longer need to screen another 100,000 compounds. You only need to using the AI model, you only need to screen 48 compounds to discover another good compound. So roughly it's more than 1,000 more efficient. So that's how the AI model can facilitate the drug discovery pipeline. A second example, which also the last example today, is for the anti-alpha viral. Alpha viral is also a tropical viral. Like there are many viral in the family. 2 examples is the chickpea and the wave. Previously, we had some experimental data for chickpea, and we have a lead, but it's only active against the chickpea, not active against the wave. So we use previous data. We build an AI model to predict anti-chickpea and wave activity. In combination with other molecular modeling tools, we designed some new analogs that is not only active against the chickpea, but also against the wave. So the AI model can, in this case, help to discover better compounds with broader antiviral spectrum. So in summary, we established this integrated drug discovery platform, and we are also looking for more external collaborators to develop it together. And it has already been successfully used to help our real drug discovery project. With that, I would like to thank many of the collaborators from Southern Research, and also many collaborators from UAB, as well as other institutions, and also some of the funding organizations. And thank you everyone for attending my talk today. I would be happy to take any questions.
All right, thank you very much, Dr. Thang. So that concludes the technical session this morning. And I would like to transfer this now to Dr. Lefkowitz, who will chair the application session.
Okay, so now we begin a series of 10-minute flash talks, 6 in the next hour. So we're going to try to adhere to the schedule. Okay, and so I first want to introduce Tan Nguyen, who is going to talk to us about methods for the analysis of cardiac single-cell RNA-seq data. Sure.
Hey, hi everyone, and happy to be here for probably 20 minutes. So my talk today is a small part of the cardiac regeneration projects, where I use machine learning and AI tools to analyze this data set. And today I just talked about the autoencoders. So why this one is difficult, good difficult? There are a couple of reasons. Number one is in cardiac disease, the main cause of the disease is a loss of cell, especially cardiomyocyte. This is a contracting unit of the heart. For cardiac injury, which is a leading cause of death in the world, you instantly lose a large amount of cardiomyocyte within a minute. And the recovery rate is so slow that it could not make up the loss. So, so the goal of the cardiovascular disease treatment is to make up that loss, increasing cardiomyocyte proliferation. And on the other hand, this event is very rare also. So in adult heart, like ourselves, we only have less than 1% of cardiomyocyte that can proliferate per year. Same to other mammals. So it is very rare event and not easy to be detected. It's different from other disease in that aspect. So, we also try other tools for single cell data for cardiac. And because of that small event, if we don't do it carefully, the toolkit might miss, might consider these key events, the proliferation of cardiomyocyte as good noise and lost this key information. So this is why we try a couple of tools and then was not very happy with those. So we come to those application of machine learning and autoencoders. So the pipeline of analysis includes multiple steps, as I show in these figures. So usually very similar to most of these other analysis. We, number one, identify the cell type in the data. And this step is actually not easy either. Why? Because it's a tissue sample. The heart is a complex tissue, and it has, each cell type has special capability also. For example, the smooth muscle cell, which is a important cell type in the heart, in specific condition, except injury, they respond, the fibroblast, I'm sorry. So smooth muscle cell makes up these, part of them become blood vessels and they can contract. And then fibroblast, which is the primary cell type contributing to scar. And scar is what we don't want in cardiac injury. So the fibroblast can respond to those injury by transitioning themselves to something called myofibroblast. This myofibroblast, can express smooth muscle gene. Those genes can do a little contractions. They proliferate. So fibroblast proliferate through these myofibroblast transitions. And in this transition, they become something more similar to the other cell type. So if these pipeline is not careful, they might not detect these, either they might not detect these changes, or they might mix up these two cell types together in one cluster. I would say this one. So this already is kind of why, another reason why it is complicated. So that's question one. Question two is analyzing the specific pathway and process that, compare between the cardiomyocyte, proliferating cardiomyocyte and non-proliferating cardiomyocytes. And sometimes we talk about the transitions because they are special cases when the heart can recover after injury. That happened when the injury was induced on the first day of the animal after birth. So that was confirmed in mouse and also in other UAB in my lab in pig. And in this case, we see cardiomyocyte proliferate. The heart doesn't have scar and fully function after 1 month of injury. So these are three things. And then how the cardiomyocyte transits from the injury state to the healthy state is also a question. Yet I probably just focus on the first two today. So coming to the key architecture, the autoencoder we have is primarily to do clustering. So most of us might know the main idea of the autoencoder is to synthesize the data set. So we have an input layer of whole genome. Here I discard the low expressing gene and choose this, for PIC, that is 12,082 genes. And then input and output, we try to make this synthetic cell at the output layer to be as similar as the input layer as possible. So in this deep outer architectures, we take the middle layers of that layer has the smallest number of dimensions. And we use that layer for UMAP, clustering, so forth and so on. So this architecture can be used in two steps. Step one, we can use us for clustering to identify cell type. And step two is to identify subset of the same cell type. We focus on cardiomyocytes. So we try that with fibroblasts and endothelial cell also. So they do find a subset of or substage of cell during those recovery process. So we compare the pipeline with many other well-known here, including cell scan PY, and we set up a couple of tests to see which one is quote unquote more reasonable for the cardiac tissue. So the first test is using these mouse data. So this data set was generated by Miao Zui, a good friend of mine also. She did the cardiac injury on 2 lines of mouse. The first line, the injury happened on the first day after birth. This mice will fully recover. Cardiomyocyte come back to life, and then things everything looks normal. The second line of mice is when the injury was, induced on the 6th day after birth. And this mice will not recover. The heart will form scar, and we see more fibroblasts rather than cardiomyocyte at the region. You see the dark over there. So the 2 lines we'll see is number one is cell type identification. So first we try to say cluster the cell, which cluster correspond to cardiomyocyte, which one correspond to fibroblast, which one to endothelial cell, and which one is immune cell, and which one is smooth muscle cells. Those are the 5 fundamental or 5 major cell types in the cardiac tissue. Then also other, depending on which heart region we take sample. So the data set we take from the left ventricle. So we only focus on this major 5. If we take some from other region with the heart, we will see other cell type also. So this is what the autoencoders produce. So we plot the UMAP, we see the cluster, and we overlap these expression of cell type marker. So cardiomyocyte, NYS7, IYI2, so they define the red cardiomyocyte. So collagen expression is over here. Hopefully you can see my pointer. Sorry, that is not. Yeah. How do I use my red pointer over here? Okay, thank you. So, so these, I don't see the figure anyway. Okay, thanks. So the fibroblast is lower one here with collagen expressions, and then endothelial cell PKM1 expression. this small cluster is an immune cell. And then smooth muscle was, this marker was colocalized, right on the top of the fibroblast. So that is basically I said just a few minutes ago, under the injury, a certain proportion of fibroblasts can express markers of smooth muscle cell. So that is sometimes many cases, these two cell types get together. Yeah. So thank you. Yeah. And then same thing with the same test with the other tool, CELRAD. And then we see all 5, scan PY, we see all 5. And then the other tool, we usually lose smooth muscle cell. And then in some cases, cluster includes a mix of cell type, which we know is not to be that way. So, so the only 3 left is autoencoder and scan PY. And then the second test is to identify. Okay, thank you. Yeah. Anyway, this is long, so so to the end, if you want to hear more about those tutorial, can go to our lab website. We have even big data set over there. What I talked to today was even a small mouse data set. So big is much better than that. Thank you.
Okay, thank you. So next we have Kareem Budwani from the Precision Medicine Institute here at UAB to talk to us about using AI in oncology drug response.
What do I do this? Should be that right there. And the first one, I think. I think that's it. And start. What did I get? Oh. All right. It doesn't show my notes. Oh, then it does over there. Okay, great. So can everybody hear me? You know what's, first of all, good morning. And I'm so glad that we got to hear from so many experts in artificial intelligence this morning, because I am an early pioneer in artificial ignorance. So about 2 decades ago, some colleagues of mine and I endeavored to create a prototype AI engine to optimize routes for delivery vans. Our goal was to reduce emissions and the subsequent impact on the environment, public health, so on. Little did we know that this journey would give us invaluable insight into the world of AI. Yes, our initial endeavor was a spectacular failure, but spectacular failures, like a college education, might cost a lot, but also offer a great opportunity for learning. So our CFO, Chris, he often reminds us that if we could learn as much from our successes as we did from our failures, we would be rich, young, and beautiful forever. And that's what that DNA word cloud says. So what did we learn from our spectacular failure? Well, we quickly realized that there were 2 vital elements that were missing. One was good quality data that was designed specifically for AI. And second was domain expertise. Mathematically speaking, because I'm assuming most of us are geeks in here, artificial ignorance is when you integrate bad data. I mean, when you integrate smart algorithms over bad data. And the sad corollary to that is that the smarter the algorithms, oftentimes the more ignorant the outcome. Of course, that wasn't that was like decades ago. Over the past 20 years, we have seen some remarkable advances. Computing capacity has grown exponentially. Costs have gone down. brilliant minds across the globe are working on innovative solutions in virtually all sectors. So we have resolved all the problems that we had in the past with AI, or have we? So despite all the incredible advances, we still have recent examples of spectacular failures across industries that serve as a sobering reminder that we still have a long way to go. From HR to finance, to media to art, there are some very disturbing examples of perpetuating bias and discrimination and disinformation. Now, what we would like to think that healthcare would be exempt from this, would be immune to artificial ignorance, because after all, it is a matter of life and death. So can we trust AI to make decisions where decisions matter the most? Okay, so here's an example from a market-approved neural network that confused the presence of rulers or scale bars with tumors. Now, there is nothing wrong with this data or these images. The data itself is actually perfectly fine, but the presence of scale bars and rulers, which are very good for humans, confuses the AI. How do I actually go to those? Can I actually go to the, oh yeah, I can, that's great. But it doesn't change anything, right? Cool. Okay. All right. Let's see if I can still switch. Perfect. Okay, here's another example where skin markings led to an increased false positive. Skin coloration also similarly leads to misinterpretation. Again, I want to emphasize and underline that there is nothing wrong with this data. In fact, this data is very good. But in the absence of domain expertise to refine and contextualize it, the AI gets confused. So what we see with the increased computing capacity, reduction in costs, is an ever accelerating push to roll out AI systems. And what that results in is transforming the old adage, which was garbage in, garbage out, to garbage in, amplified garbage out. Obviously, the visceral reaction to this is to question whether AI is doomed to fail into the trap of artificial ignorance. Many leading experts and thinkers, not me, of course, but have suggested that we pause AI development. But realistically, is that even an option? Particularly in fields like oncology, and I'm revealing my bias here because my background is in oncology. In fields like oncology, where the need for improved diagnostics and treatments is urgent and critical, can we afford to pause AI? I think it should come as a surprise to no one in here that the public health burden of cancer is immense and continues to grow. Solid tumors remain particularly intractable because every tumor is unique in its composition and how it responds to even the same treatment. So we must find more effective ways to match treatments to tumors. And this need for drug response prediction, DRP, and I apologize about adding to the alphabet soup, but DRP is not just for the bedside, but also very needed upstream in clinical trials and drug discovery. I think you might be familiar with this image, but even today, over 90% of new cancer therapies are unable to complete the molecule to market journey. And this despite nearly $100 billion of investment every year. So it is clear that we need better DRP throughout the drug discovery and development process. And guess what? AI has the potential to revolutionize this process. And this is why I believe it is vital that we continue to invest in AI development for oncology DRP, because I believe that the potential gains far outweigh the potential risks if we can address the underlying issues. Okay, so we are faced with this difficult choice. On the one hand, we want to accelerate AI in oncology and risk the potential pitfalls, or on the other, pause AI development and miss out on the incredible potential that can be leveraged from AI. So a classic rock and a hard place. But don't worry, I will not leave you on a cliffhanger. There is a way to harness the power of AI while avoiding the pitfalls of artificial ignorance. It is a lesson I learned a long time ago, but it still rings true. The example that I shared earlier, yes, I cherry-picked them to make my point, underscore the vital importance of good data that is generated for AI and strong domain knowledge. The lessons from 2 decades ago are still relevant and can help us have our cake and eat it too by mitigating this issue of garbage in, amplified garbage out. Because our goal is not just to crunch numbers, but to make a meaningful, tangible impact in the lives of patients. So how do we do that? Most oncology DRP systems, how much do I have? Oh, all right. So most of these systems that you see use traditional in vitro and in vivo platforms, and there's nothing wrong with these data sets, except when you think about it, that all the drugs that make it to clinical trials have been shown to be successful in these models, and yet 90% of them fail in clinical trials. And also, most of these models are hypothesis-based. They're not p-hacked. That's a good thing, but that also introduces the PI's bias in how the data sets are generated. So this is the initiative right now that we're working on. It essentially integrates the established and emerging models with tumor specimens and close derivatives of tumor specimens for developing more sophisticated oncology DRP, because in these supermodels, the key is to make sure that the data sets are both relevant and also continue to have domain expertise. Oh, time up, I guess. So I'm going to skip this one, but I'm here to have a conversation later. I want to thank our partners, and I want to thank you for listening to me and hopefully joining us in this journey. Thanks.
Okay, thank you. So next up is Dayan from Department of Computer Science to talk to us about us talking to each other across disciplines about AI.
Thank you. Oh, thank you.
Yeah, the first one. Yeah, I think it's similar. Oh, this is hidden. I think it's coming. I see. Still going. Okay, thank you. Good morning, everyone. My name is Dayan. Also, you can call me Daniel. I'm totally from the computer science side, all right, and not having any secondary point with the medicine, health, or even biology. So, but I do explore a little bit into health and medicine side and try to seek some collaboration. So the main purpose of this talk is I would like to introduce some of the research, especially done in my lab, and so that when you are preparing for your research or even just the ground proposals, you can think about, hey, maybe Daniel is someone you can talk to. All right, so I will, in this talk, I'm aware we are 5 minutes late, right? So I will really be fast. I will first talk about some interdisciplinary research on AI and then on big data systems, right? AI, mainly you want to accuracy, right? And also you want to maybe interpretability, and for big data, you want to speed, right? Especially the genome data that are in really large scale. Finally, I will introduce what we do in our lab and our qualifications.
All right, so the first project I would like to mention about AI, right? Not big data. Okay, so AI. So we do some research. I try to focus on the medicine and the health, but some of the research are interdisciplinary, not totally in medicine and health. Okay, this one is a flood extent mapping. It's more like environment science or climate change. Okay, so here is a Google map of I think in North Carolina, there's a region which were flooded by Hurricane Harvey in 2016. So this is a normal time image, and then when the flooding comes, you can see a lot of the places are flooded. And our goal is, for example, to predict which pixels are flooded, right? Marked in red, and the blue pixels are dry. And these problems have a lot of implications, right? And social impacts. For example, you want to schedule a disaster rescue, and for climate change, you want to see where places are under the water, right? So we developed an AI approach where firstly we need an annotation, right? So and then after annotation, we have the training data, a lot of the terrains. Then we build this kind of segmentation model, and finally the segmentation result may still be noisy. We use a graphic model to cleanse them. And here's a tool. I think we have a video here. Maybe I can play it. Yeah, that we develop for 3D, annotation, because we only have those satellite images and maybe called the elevation data, DM data, but we don't have annotation which part is flooded, which part dry. So we can quickly annotate by, for example, if you say these pixels are dry, we can climb up, hill, right, and all these pixels will be annotated. If you think some places flood, it will climb downstream, right, and say those places are flooded. Okay. Let me see how to finish. And yeah, so we have some, for deep learning, basically design those models and how to fuse them to better match your input, right, and extract those semantic features from raw data, right, and then you have the loss function you want to develop specific to your domain application. Like here, we are trying to use the elevation data to penalize, for example, in case 2.1, if you know that the neighbor pixel, the red one, is flooded, but you predict the blue one to be dry, right? Then it's impossible because the water will flow down, and you need to penalize loss function design. And here's the annotation map that finally we use, for example, can be for model training, and we also get very good results for training. Okay, so now I want to switch to some projects that are more relevant to AI for medicine and health. And one example is a collaboration with a prior professor. I think he moved to Texas from Department of Chemistry. And what they are doing is called this iPSC cell counting, right? Because they want to see if this is kind of a cell that can generate a stem cell, then can maybe do a lot of things there, right? So, and they want to see if this cultivation for 30 days is successful or not. So they have this petri dish. They kind of cultivate the cell and let them grow, and finally they need to count and see if it's successful or not. Right? And we developed some model. I won't go into the details because of the. I don't want to make it too technical, right? So another thing is, for example, we have neural imaging data, right? So we kind of break them into regions and see how they kind of correlated with each other, right? Functional connectivity. And then we use a graph neural network, right? So mostly in deep learning right now with raw data, right? Whether it's a graph neural network, have the network structure, like so in structural biology, you are using image data like CT or natural language, right? Just like Matt mentioned, reading a lot of text. And we customize on the models and using feature fusion finally to get good results. And also, this is more like a tweet, right? So people are talking about tweet. We want to find, for example, whether there are mental health issues, right, with some people, and maybe this can help early intervention and help these people. All right, so the next is about the big data systems, right? So because now in bioinformatics, computational biology, there's a lot of data, right? So we do a lot of, for example, one important source is structural biology, right? A lot of the graphs. So we have a lot of systems that are developed for graph analytics. This is more for iterative analysis, right? Like page ranks, those kind of computation, ranking your biomolecules, right? And then we also have this, so this is a particular piece of work that I would like to introduce, where we published in VLGB in 2014, really early piece of work. will get a lot of citations and was cited by another tutorial as the research piece. And then our work get noticed by Robert Harding with a Turing award in 86. And we had the Dexter seminar, which is a computer science gathering event held in a castle in Germany. And we also have some correspondence discussion. And this our work, the top work motivated our paper, which then the method is then using our method. I think this is a clever work also with Jay. And if you ask me what is my more than 50% of the effort, right? It's really in big data system design. So we pioneered the T-Thinker framework, and we have many tier one, dozens of tier one publications, and apply them. So because I'm still a assistant professor, I need a core research, not just interdisciplinary, but now I'm explore a little broader and hopefully can find more collaborations and have some impact in real applications. And here's some example of our system. So our system mainly work on this kind of, you can see this is kind of denser graphs, right? So called a quasi-clique, and we have the direction where if you point to it, it will be blue, right? If you point out, it will be red. And we can search really fast, and this is maybe 1,000 times faster than existing method. Another example of the tool that we developed is called a frequent subgroup pattern mining, where if you have a big graph, you have many small graphs, networks, right? So you want to see what are the structures, and again, we can be maybe hundreds of even 1,000 times faster than existing work. And you can search for what pattern you're looking like, interesting, right? And then this is the patterns, right? So then you can open, let's say, hey, where are those patterns really appear in the data is a big network, right? Because the patterns, if you find, you just say, if I find 1,000 occurrence, it's frequent, right? But you don't need to find them 100,000, even if they're, but when you actually examine them, you need to open them and check in the details. Yeah, let me see. Yeah, so another example, this again, not in medicine and health, it's about transportation simulations. This is a collaboration with Professor Sisipiku from CCE department from engineering side. And they have this STRIDE project. It's a UTC center for Department of Transportation. And they want to do this transportation analytics, especially simulation for the Birmingham region, right? So we have actually, then she finds me, we collaborated, and we provide IT support for them, basically, for all the data science and analytics. And then we actually also get 3 grants out of this. Yeah, so a brief introduction of my lab. So this is me, and again, my area is core computer science, right? Algorithm, right? We talk about time complexity, speed, right? And machine learning, right? Models, and also systems. And regarding ranking, like in all areas, we are ranked 130, but I have like 22 publications in the tier 1 venues, and in database only, data management only, I can be like bring our department to 50 in US. So, and some of my prior students, like Guimu Guo, John Rowan University, assistant professor, and Jalal, this summer will be graduating and join another university as assistant professor. And these are all other students currently in my lab. Like Luhan was from the UPenn, mastered in computer science, and got a belated fellowship, and has already just the second year, get a lot of publications. And also the others working in different areas. And some prior students I worked with, like Ilu, previously with the Harbin Institute of Technology, went to Hong Kong because I moved from Hong Kong directly to UAB. Right? So he worked with me and then got me to MIT. And there another student, for example, went to UPenn for PhD and recently got the University of Toronto as a professor. Yeah, and this student is in Auburn with Dr. Wei-Shin Ku, who was rotating in NSF. So I helped a lot inviting that student. We have a lot of AI conference, you can see, right? So, and he also got a assistant professor this year and will be joining this fall. So yeah, so I'm really looking at collaboration, right? So when you look at your AI projects in medicine side, you may think about, hey, maybe I can talk to Daniel in UAB, and maybe something interesting can come about. And I would be very interested in understanding the domain knowledge and design those AI models or even scalable solutions for you guys. Okay, thank you.
Thanks a lot. Okay, and now we move on to Rahul Sharma, who's in the Informatics Institute here at UAB. to talk to us about drug development and the use of AI.
Hi, everyone, can you hear me? I'm Rahul. This is a presentation for a library, Python library, but it can be. Hi, I'm Rahul, and this is a presentation of our library, which we have developed while developing AI-based preclinical trials and clinical trials technology. So this library is available open source, and I'll just give a brief information about it, and I'll try to make you excited to use this library. So I'm kind of marketing it. So let me start my pitch. I'm working with Dr. Chen and a developer named Prashant Sharma. So this is my content. I'll talk about the motivation behind this, drug feature extraction, why we need it. And then I'll talk about the library a little bit. I cannot give the demo right now, but one can reach me out in the breakout sessions, and I can discuss how we can use it, and then future works in the conclusion. So the main motivation behind this work is want to accelerate your AI-based drug discovery. Data is important, and you are interested in accelerating, you want good data. But when it comes to AI-based drug discovery, the word drug is very important, and how to process that drug data. Drug data is available in different formats. I'll discuss that right in the coming slide. So you are struggling in predicting drug properties. Yes, prediction problems are there. Searching for new drug candidates. All these things, these motivations that I have listed, it's an endless list actually. So how do we do it? We were also struggling with the same. So we came up with a solution and developing a feature engineering library for us. So this is how a simple format. There are many ways to represent drug. This is one is on the left-hand side, one is the 2D representation of the drug. If you can see this here, this 2D representation, and this is the smile representation on the right-hand side. So how do we work with these? We can work with these as image analysis, but we took a different approach. We are now using the drug smiles. Does computer understand these drug smile directly? This was the question that was posed to me. So computer understands only vector representations. So we started working on how to represent these drugs. There are different ways of representing drugs, fingerprints, the most commonly used methodology, but we developed our own methodology using natural language processing. So the library that we are developed is DrugSmile FET. It has two modules right now. One is NLP-based methodology, which I'll show an animation in a short while, and Morgan fingerprints. So Morgan fingerprints is the molecular representation technique that is available through RDKit library. People can use the RDKit library or Kimball, or they can come to our DrugSmile FET. It's a Python library, so you can use it. It's a low-code Python library, so you don't have to do a lot of computation. Just provide drug smiles as an input, and you will get the output as a feature vector. Second thing is this. Natural language. This is the innovative part that we are doing, and we have very good results when we were performing our drug response prediction experiments for preclinical trial technology that we are developing. And this methodology is also available with this library. So this is the uniqueness of this library. This library will be comprehensive. So you can have all sort of feature vectors that we have. There are like around 25 of them. We are one by one, we are bringing it to one place, and it will be a low coding library. Besides this, how you can use it. So one way of using is you are a Python programmer, you can use it. So you just provide the drug smile. Just a moment. This is too fast. So this is You import the Python library, and then you will get the outputs, and then you can apply this to your AI models. So we are not providing any kind of AI-based AI capability. We are actually providing a methodology where you can transform your data into feature vectors, and then you can use that data for you. So it's very easy to install using pip. It's shown over here. Oh my God, this mouse is flying. Yeah, it's here. Second one is UBride. So UBride is going to provide a web interface. And I've already developed the tool, but I cannot give you the demo right now. I have the tool with me, and we are in a process to host it with UBride. So what will happen over there? You have drug smile data. We just provide that drug smiles to us with the drug names, and you'll get back a feature vector. So it will be, mostly it will be in CSV, what we'll try to process all the different kind of data formats that is available to us. This is one way of representing this. Why drug feature is important. So these are some components where you can use it. So you can use for drug target interaction prediction. You can use for toxicity prediction, drug-drug interaction, precision medicine, drug repurposing. List is high. In one of the talks of precision medicine, they have asked, they are using it. So I'm kind of marketing my library right now. So use this library, make fullest use of it. If you find it interesting, use it in your projects. If you want to incorporate in your projects, tell me, I can provide APIs for it, which is the next stage. In UBride, right now, this is an open source MIT licensed Python library. You can use it in your own work, or you can use UBride. So in UBride right now, we are working on the interface, but at the same time, we'll be providing you the API. So if you are not a Python programmer, don't worry about that. We'll provide you APIs. You just integrate those APIs in your platforms or whichever language that you are using, C++, Java, R, whichever language you have, and then you can use it. And feel free to contact me. Dr. Chen is hiring, so please join our lab. We are working tirelessly on AI-based drug development, and we are looking for talented people to join our team. Thank you so much. Any questions?
We actually have time for a question. Anybody does?
I timed it well.
Otherwise, we'll move on. Thanks. Pleasure. Okay. Next, I'd like to introduce Timothy Fisher from the Department of Biology at Georgia State to talk to us about use of AI to predict neoadjuvant chemotherapy response in triple-negative breast cancer. So is this Zoom?
Hello, everyone. Good afternoon, everyone. My name is Timothy Fisher. I'm currently a senior PhD candidate in Dr. Ritu Anij's lab. She's currently a UAB cancer biology professor here. I'm also co-advised by Jun Kong at Emory Winship Cancer Institute in his biomedical imaging lab. And I'll be giving a talk on machine learning approaches to predict neoadjuvant chemotherapy in response to triple-negative breast cancer patients. And this is a very high-level overview of 3 years of research. Hopefully I can excite you the way I'm excited about it. And so in breast cancer usually starts in the breast tissue, depending where it's at. It could be in the lobules or it could be in the ducts for ductal cancers. Out of all cancers, breast cancer accounts for about 30% of all 30% of all cancers. And out of those breast cancers, there's different subtypes. There's hormone positive, which accounts for 65 to 75%. There is HER2 positive, which accounts for 15 to 20%, and also triple negative breast cancer. And that accounts for 15%. Triple negative breast cancer is the absence of these three molecules: estrogen receptor, progesterone receptor, and human epidermal growth factor 2. And so in my project, I'll be focusing on neoadjuvant chemotherapy because it's currently the golden standard. There is no FDA-approved targeted therapy for triple negative breast cancer. However, if you do express PD-L1, which is programmed death ligand 1, you're able to get immunotherapy. So in this study, once again, focusing on neoadjuvant chemotherapy, we have 2 cohorts. The kind of responses we're looking at is a good response called pathological complete response, and a bad response called residual disease, abbreviated RD. And we have 2 cohorts. The first cohort, for the good response, we have 51. In the bad response, we have 34. The validation cohort, we have 38. And the second cohort, we have 41 for RD. And so some basic background, comparison between TNBC and other breast cancers. The overall survival, you can see, is a lot worse than other breast cancers. And similarly, the overall function as a response to neoadjuvant chemotherapy, when you have this bad response in triple negative breast cancer, you see in the red line here, you have a lower probability of staying alive compared to, let's say, if you have a good response and you still have triple negative breast cancer. So it's really key that we identify those patients that have those good response based off their tumor biology and the different components there. So in summary, we're looking at breast cancer tissue, and we want to be able to predict the NAC response in triple negative breast cancer. And we would like to do that by taking the tissue samples taken when they're getting biopsies and looking at the tumor. And this is before they're given neoadjuvant chemotherapy treatment. And we want to be able to predict the good response or a bad response. So those endpoints we're looking at is NAC response. The measure we're looking at is the histological components. The problem is there is a lack of knowledge in triple negative breast cancer heterogeneity, which make it very difficult to predict who would benefit from the therapeutic agents. And so I would like to distinguish between the histological components and hematoxylin and eosin stained whole slide images on triple negative breast cancer core needle biopsies to identify those histological features of tumor microenvironment that can predict NAC response. And so we partner with pathologists to annotate a whole slide image, which is a large image file, hyperstacked in a TIFF hyperplane. And we have a software which I'm a contributor to. It's called QPath. I developed some of the scripts in Groovy for it. I look at a whole slide image and I train the pathologist to annotate those different areas, the histology. And so once we have those coordinate points, then we map it back in a programming language. It could be Python, R, MATLAB, whatever. And then we put those back onto the original image. This is a downscaled version at level 3. So we could read it in and all the coordinates. Then we break it down into tiles. And we want to see those different areas and be able to partition those regions of interest from the pathologist. And so at the end of the day, we have those tiles and we create a classification map of those tiles. And that represents the whole slide image. And we're trying to capture the tumor microenvironment. So we annotate for those different regions. In this example here, you see stroma in green, and you see tumor TILs in purple, you see benign tumor in blue, and you also see blood vessels in red. We have 16 total classes, and we have two pathologists that annotate it. The first step is to train a classifier to again, take those tiles. We're doing 224 by 224 tiles. And then we're putting that into our first step, which I created myself, this whole pipeline. We did color normalization and color deconvolution, and that's to normalize the stain across different cohorts. In the color deconvolution step, we take the hematoxylin stain, which is a grayscale version of the image, and captures most of the tumor microenvironment elements in that tile. And we extract the texture features or just representation of what that tile image is. So at the end of the day, we have a feature spreadsheet of texture features. We call it a feature vector. and we input into our different machine learning models. And this is pretty much like a small annotated pathologist to identify those areas of interest from those 16 classes we have. And you can see on the picture on the left, that's how it would look like once you have the output from our machine learning models. And so once again, we have a small annotated pathologist with our ML classifiers. We have a tile. We have 80 texture features in total. We have a feature vector for each tile, and then we put it into our path, our different models. And so in this example here, you see on the tile on the top left, this tile is being inputted into each different classifier. And so you see about 66% for the first tile is being labeled as cancer. So that would be labeled as a cancer tile, and it will be a part of the cancer classification map. And you can see here, this little red dot, it will be shown that this tile will be added to this classification map. And then we can combine that with the different histology classes and create a whole slide image annotation, which we refer to as a classification map. And so the results are between the different machine learning models. We had the best model from radial basis function, SVM, with 87.2% accuracy, and we used a stratified KIG cross-validation with 8 folds. This is the confusion matrix of each different histological label. And this is the performance metrics like sensitivities, selectivity, recall, F1 score. We had similar results in our validation cohort. We did the same pre-processing steps. We did the same analysis, used the same first step of the pipeline. Once again, we're just trying to identify those, in the new cases, the histology based on the tile method. And so this is the second step. We take that histology classification map and we look at the patient whole slide information. And so we want to capture the tumor microenvironment, and the way we do that is by doing a pairwise combination of 2 different histology groups. And we have in this left here a blood vessel in this map and benign tumor. And on the right, we have tumor TILs and stroma TILs. And so in the first cohort, we had 85 whole slide images. In the second cohort, we had 79. And we had a total of possible combinations of 112. And so we're looking at the tumor microenvironment spatial graph-based features, and that's based off a pairwise comparison. And so in this example here, we have stroma and tumor, and we are making graph constructs using the methods of random geometric, spectral graphs, and minimum spanning trees. And so in this small example here, you see a stroma node, and then we're trying to connect the stroma node to the tumor node, and we're taking the tile size that was 224 by 224 and counting the distance from the tumor node. And we're using a Euclidean distance to measure that. And we take that feature vector and we then do feature selection. We go through a round of feature selection and we see based off a relief F method, what ranks the most. And based off of literature, we are adding the NAC response information, but the relief F feature selection algorithm only uses the importance weight of the neighboring groups. So the next step is just to classify it. And once again, the best classifier was 83.5%. We use leave one out cross-validation. At the end of that, we compared the different cohorts and we have similar results in the confusion matrix. And at the end, we have this attention map, which shows the high attentive areas for predicting NAC response. So our model is incredibly cheap and quick. Our model identifies tissue areas in H&E whole slide images at high predictive value for NAC response. And our findings improve clinical decision-making for TNBC patients. Automated NAC response relevant histological components, and our model accounts for spatial relationship in the tumor microenvironment to classify NAC response. And so takeaway, our machine learning pipeline can robustly identify clinical relevant histological classes that could predict NAC response in TNBC patients and may guide patient selection for NAC treatment. This is a smaller part in a bigger project in Dr. Ritu Anij's lab. I'm looking at the angle of TME and whole slide images, but we're also looking at proteomics, the whole exome sequencing, RNA sequencing, and combining it to enhance predictive power. And I want to thank everyone that I work with, the Dr. Ritu Anij's lab, Dr. Jun Kong's lab. My background, I have a master's at Morehouse School of Medicine, so I was about to get an MD degree, but I decided to go into research because I'm really curious on how I could combine technology and cancer research. So I like to use all of that experience to help the people I really, so passionate about the cancer. So thank you.
Thanks. Okay, so to end up the session, we have Emma K. Schmidt from the Department of Radiology and Biomedical Engineering here at UAB to talk to us about deep learning models on kidney disease.
All right, can everyone hear me? I'm the last talk between you and lunch, so we'll get it done quickly. Today, I'm here to talk to you about deep learning-based automated kidney and cyst segmentation for patients affected by ADPKD, and we're focusing on single versus multi-institutional data sets. So the whole point of today, everyone knows AI has the potential to help us save time, save money, make connections that maybe we can't see as humans in data sets. And we want to start using it as soon as possible in medicine. What do we need to make good AI? Data. But medical data hides behind a lot of red tape and patient privacy laws. Unless a larger organization has provided that information for you, it's hard to ask people for that information. And the point of my project is to stop here and ask, well, how much data do we need? Do we need to ask other people for their data, or can we make good, highly specific models that will work well on our patients with our protocols, or do we need to start asking other people for their data, start jumping through those hoops before we start coding? So a little bit of background about ADPKD, autosomal dominant polycystic kidney disease. It affects about 12 million people worldwide, 600,000 here in America, and it is characterized by this rapid, aggressive growth of cysts in the kidney until it overtakes it and you are in end-stage renal disease. ADPKD, we can track it, we can identify it, but we don't have an approved methodology for tracking true progression. Now, the NIH has decided to fund a longitudinal study between 4 different universities or 4 different institutions to gather as much information, as many biomarkers as possible to begin to understand how to track ADPKD progression so that we can start coming up with clinical solutions for ADPKD. So in this, we found some measurable factors such as renal function, GFR. My focus in this CRISP cohort by the NIH is looking at the imaging. And you can see on the right some T2 weighted MRI images. And what we do with these images currently is we have either a radiologist or maybe a med tech or a semi-automated approved method go through these 3D MRI volumes and circle the boundary of each slice. We stack those back together and we get a total kidney volume. We can track that volume for the patient over months, maybe years, to track how large the kidney is getting and maybe map that to when we really need to do something about it rather than manage symptoms. Now, the other potential we can do with especially T2 weighted MRI is begin looking at these cysts. But as you can see from the image, it's going to take a lot of time. But that's a perfect opportunity for machine learning to do this automatically for us. So to set up my project to answer this question, I took the 4 institutions that the NIH CRISP cohort had, Emory, Mayo Clinic, UAB itself, and Kansas University. And I created 5 different training sets to create 5 different models. First one being a multi-institutional set. We have 80% all of the data available to us, and then we put 20% aside for a test set later on for validation. And then we created 4 other training sets with just that single institutional data, 80% of that institution. We fed that information into just a basic, robust UNet basis of most image segmentation, fed it into a UNet, and then we took the original MRI image, that kidney segmentation, and then we fed that into another UNet to get the cyst segmentation. After that, this was done on 2D slices, so we stacked those back up into 3D volumes and took the dissimilarity coefficient as a measure of accuracy. And then we began plotting those dissimilarity coefficients and analyzing the results between multi-institutional results and the single institutional results. For the kidney segmentation, we had great accuracy overall. And in an ANOVA analysis, we found that there was no statistical significance between the multi-institutional model and the single institutional model on their own patients. However, as you can see on the right, I have all of the different institutions overlaid on the same patient, tested for cross-functionality. And we do see a bit of reduction in cross-functionality, but on your own patients, you really only need your data. You don't need to ask other people for more data. However, we do see a complete reversal of this in the cysts. In the cyst segmentation, we saw an overall lower accuracy, but the multi-institutional model in the ANOVA analysis did significantly better than the single institutional data sets on their own patients. You see the same loss in cross-functionality, but overall, some of the reasons that we think maybe the multi-institutional model did better, just more examples, different disease state progression in different institutions. Some may have very early onset, very itty bitty cysts, hard to pick out. Some of them might have more advanced stages where the cysts are easier to find. But overall, the multi-institutional model did do better and was more accurate than the single institutional data sets. And so the conclusion of this, these are just the initial findings of the project. We're hoping to publish this, but if you're looking at big boundaries, one organ system, even if it's irregular, like these kidneys are not all the same size or same shape, you can do that with your own data. UAB was our smallest data set of 15 patients over 4 years. This is a pretty small data set on a pretty rare disease. So we were able to have good accuracy with just a single data set. But if you're looking for something like cysts, something highly irregular, varying in size, varying in number, you are going to need to start asking other institutions for their data, for their cohorts, or look at like NIH funding this longitudinal study to begin understanding how we can use medical learning or image segmentation to automatically track and isolate these items. So some of the things now that we've found these initial findings, find the kidneys, can't really find the cysts. We're looking at how we can use other types of data augmentation to help enhance these single institutional sets. Flipping, grid distortion is what I already have, but there are definitely other things that we can do. We're looking at more advanced architectures. I have someone in my lab who's looking at the NNUNet, most kind of cutting edge for image segmentation. And then we're also investigating, why are we losing this cross functionality? Why does Emery's model not work on the Mayo Clinic's model? Are there differences inherent to the MRI machines? Is there something happening when we're transferring that data to someone else? And then also what makes an image outlier? Let me go back a couple slides. So as you can see, that Emory patient, it's pretty bad. So, is that an image outlier? Should we include that in our training set when we're looking at investigating this disease? I threw all of the data that I had at it, but that's something that we can begin to look at when we're training on small data sets for a highly unique disease that you might have to ask other very specific cohorts for their information from. All right, that is the end of my talk. I would like to thank the PKD Foundation for funding this research, as well as this collaborative effort between BME, Radiology, and the Mayo Clinic up in Rochester, Minnesota. Thank you.
Okay, thank you. So this is the end of the flash talks, and now we have lunch in the poster session and back in this room at 1:30. Jake,
Yeah, I want to thank all the speakers and the session chairs, especially Dr. Higgs and Dr. Lefkowitz for doing a wonderful job. And if you ordered lunch beforehand, you can go out and pick up your lunch. If you did not, feel free to roam around, and there are plenty of cafeteria. But do come back at 1:30 because that is going to be an interesting topic. If you're ever curious about how ChatGPT works, John Osborne is going to talk about large language models in AI and try to actually find out what's going on behind the scenes. For those of you who want some entertainment, I promise you I have a 3-minute video I didn't show before the keynote. You're welcome to stay and get some entertainment. All right. So. Yeah, so if you're poster session judge, hang around. Where is that?
On the another.
Yeah. Hold on. Yeah. Where is the, like my introduction? No, not tutorial. Open, yeah. Yeah. Can you just share? Oh, it's already shared. This is a very interesting dialogue I found online. So let's see. Let me play.
Hey, how you doing? Am I like 1 or 1:30? What is it? 1:30, okay. I have I was wondering, I'd make sure my
Hi, Steve. Hi, Elon. How have you been lately? Your call quality seems to be not very good, and you're also drifting around.
Hang in there, Steve. I can't use FaceTime here. Did you know that AI Talk is making me talk to you about artificial intelligence? This show really loves self-deprecation. So, Steve, what do you think about artificial intelligence?
the one that's on blocks is not so good.
I believe it could be humanity's biggest existential threat. Just imagine the AI behind your Siri turning rogue.
Oh, come on, Elon. I know about your recent pessimistic attitude. I've always believed in blending technology with humanity. AI is just another tool for us to enhance our lives. Remember, it's humans who give Siri her purpose. Elon, have you ever considered that maybe your fears about AI are just a projection of your own ambitions? I mean, you're trying to colonize Mars and revolutionize transportation on Earth. Maybe you're just worried AI will beat you to it.
Give it up, Steve. When it comes to ambition, you were the one who came up with Siri early on. I can't help but think that if Siri had been a little more advanced, you might have called the iPhone the I know everything.
Oh, Elon, I just hope people can enjoy the stylish design and user experience of iPhone instead of being enslaved by them.
Enslaved, you say? If I remember correctly, people were so addicted to their iPhones that they would walk into walls while texting. My Teslas can drive themselves without smashing into anything.
Touché, Elon. What exactly do the news reports about autonomous driving accidents refer to?
You're missing the point. It's not about the cars, the rockets, or even my lovely Starlink satellites. It's about making sure we don't create an AI so powerful that it decides we're irrelevant.
My dear Elon, I think you're getting ahead of yourself. AI is a tool, not a sentient being, and like any tool, it can be used for good or evil. Remember the Apple philosophy? It's all about balance.
Balance, huh? Funny you should mention that, considering the wobbling iPhone users on Earth. Anyway, I'm not against AI, but we must ensure it serves us and doesn't spiral out of control. Sometimes I worry that they will possess human-level thinking ability. Just look at GPT-4, it's like a silicon-based Shakespeare.
Elon, what about consciousness, empathy, and intuition? Can AI truly replicate the human experience?
Steve, it's all in the algorithms. Deep learning networks like GPT-4 use transformers to process and analyze vast amounts of data. By leveraging attention mechanisms and self-attention, AI can understand context and make decisions, just like us mere mortals.
AI is still bound by the limitations of its programming. It doesn't have the ability to question its own existence, ponder the meaning of life, or argue about whether pineapple belongs on pizza. The human mind is a beautiful, chaotic mess. AI, on the other hand, is built on ones and zeros.
Steve, my friend, have you not considered that we're also built on a code of sorts, our DNA? When you break it down, we're just organic machines, and AI is simply a new form of life.
But can AI experience the sublime beauty of a Bach cantata, the profound sadness of a Van Gogh, or the transcendent joy of a perfectly designed iPhone? I rest my case.
Who's to say that one day AI won't develop its own sense of art and culture? Neural networks are constantly evolving, learning from their mistakes, and adapting to new information. Maybe GPT 10,000 will be the next Mozart, or even the next Steve Jobs.
Elon and Steve will continue to discuss the emotional and creative capabilities of AI. Please stay tuned to AI Talk.
抖音